Ну все, вроде началось. Скажите что-нибудь, наверное, чтобы звук. Звук с камеры. Плохо. Никому.
1, 2, 3. 1, 2, 3. Один, два, три. Стал лучше, хорошо. Значит, но стало лучше или стало хорошо? Или... Okay, well, let's assume it's working. Today we continue what we started last week, namely we want to understand how to express the signature of a manifold as an index, as the index of an elliptic operator, and then we'll talk a little about some other applications of elliptic operators. Let's remember where we stopped. So we have we suppose we have a manifold which is smooth, and we assume, as we often do, that the manifold is oriented, does not have a boundary, and is compact. Okay, so what else? We have the drum operator, which we complexify and let's complexify the drum operator. We'll need it at some point, and if X is Riemannian, then we have the joint operator. And the sum of the differential plus the joint is elliptic. then by taking the square, we we have another operator, which is the Laplace operator, and since we have a metric, we also have the Hodge-Star operator. And the operator squares to it squares to something, and the something is minus 1 to the p. On p forms, if the dimension is even, and this will suffice for our purposes. Okay, now we want to construct another operator, which we call alpha. It's basically the same as the it's basically the same as star up to multiplication by something. And the idea is if we have something which squares to minus 1, then I something squares to 1. And so we can multiply the Hodge star by I to some power. And basically, here we don't even need to assume that n is even. I squared is minus 1. It doesn't matter whether n is even or odd. And by substituting some exponent here, we can make this thing square to 1, which we do. And starting from this alpha, we construct two subbundles of the exterior algebra. And these are complex vector subbundles, and we explained it last week by noticing that both subbundles are in fact induced from the same principal bundle as T upper star of X, but by using different representations of the orthogonal group, or a special orthogonal group. Now I want to construct an operator which goes from sections of lambda plus to sections of lambda minus, and vice versa. Okay, and this is where we stopped. We did check that alpha commutes with the Laplacian, but there is one thing which we didn't check, and this is this formula. Alpha anti-commutes with the operator D, and I don't want to check this formula. I want to say that we have all ingredients for checking this formula, and then it's basically a straightforward calculation, which is not very illuminating if one does it on the blackboard. So let's look at the formula again and see whether or not we indeed have all ingredients for checking this formula. There is one thing which we do need is, and this is the formula for D, the formula for D star, and the formula for D star. And the formula for D star is up to sign star D star. Okay, now the sign is always minus if n is even, and it's something if n is odd. Oh, sorry. Yes, thank you. Yes, this is supposed to be alpha. And my claim is that this formula implies that D takes okay. Lambda plus to lambda minus and vice versa. What does this mean? Well, this means that D takes a section of lambda plus to a section of lambda minus. Okay, so we get operators d plus and d minus, which is just d restricted to lambda plus, lambda minus. And each of those is the adjoint of the other, which we saw last no, not last week, but we did see it at some point. Basically, we use the fact that d plus d minus is self-adjoint, and then we use this formula where omega 1 is a section of lambda plus, and omega 2 is a section of lambda minus. And then in this expression, this product cancels, and then in this expression, this product cancels, and we get the adjunction formula. Okay, now the index of d plus is minus the index of d minus, and this is again something which we saw for elliptic operators, or more generally for operators between Prey-Hilbert spaces, such that the image is closed and complementable. So for our purposes, if we know the index of one of these, we know the index of the other one. So let's focus on d plus. The index of d plus is the dimension of the kernel of d plus minus the dimension of the kernel of d minus. And this is again something we saw a few weeks ago. The idea is that the kernel of d minus is the kernel of d minus is isomorphic to the co-kernel of d plus. And again, we proved this when we discussed some general facts about elliptic operators, and this uses the fact that all operators which we have here, namely d plus and d minus, are elliptic. Okay, now let's remember that we also have harmonic forms. These are the elements of delta, which is the same as d. Okay, now I claim that the kernel of d, the kernel of d plus and d minus is the same as the kernel of d intersected with lambda plus, respectively, lambda minus, which is sort of clear because d plus or d minus is the restriction of d to lambda plus and lambda minus, respectively. Well, which is the same as harmonic forms intersected with lambda plus and lambda minus. Which one? The first one? Yes. Well, d plus is d restricted to lambda plus. By definition.
No, lambda plus is eigenspace of alpha.
Yes. And d, so we have well, what does it mean? What does it mean restricted to lambda plus? It means restricted to sections of lambda plus. So if I have a section of lambda plus, then d of the section is a section of lambda minus, and vice versa. So now. How do I define d plus? I take a section of lambda plus and apply d. And I get a section of lambda minus. And so I get an operator from here to here.
No, we define d plus and d minus not like that. We took even forms and odd.
No. We take we take this d, which acts on which we view as an operator from lambda star to lambda star, the direct sum of all forms. Then we forget about even and odd, and And although maybe at some point I used the same notation I used the same notation for even and odd forms, which is bad. And I don't argue. But anyway, there's only so many symbols in the alphabet, so at some point at some point it makes sense to change the notation. Well, let's use lambda plus for the eigenvalue +1 of alpha just today.
And in general, the elements of lambda plus and lambda minus are not homogeneous.
In general, no. There are just some collections of forms of all degrees. Okay, so we have D plus, which transforms sections of this subbundle of what subbundle of the exterior algebra of T upper star of X to this subbundle. And we have D minus, which is the joint operator and which goes in the opposite direction. Okay, now does this formula make sense now? Okay, now we want to calculate the dimensions of these spaces, and we want to prove that the dimension of the kernel of D plus minus the dimension of the kernel of D minus is the signature. Okay, now there are two cases. The first case is P is not equal to the middle degree. Okay. Let me write it like this. If P is not the middle degree, then alpha interchanges lambda P and lambda n minus P and squares to what? Squares to 1. We know that alpha anti-commutes with D, and also alpha commutes with the Laplacian. So alpha preserves alpha preserves the harmonic forms. So alpha induces a map from HP plus Hn minus P to itself, which again interchanges the two summands and squares to 1. Okay, now my claim is the plus 1 eigenspace of this map. So, this map squares to 1. There are two eigenvalues, plus 1 and minus 1. So the plus 1 eigenspace is eigenspace of this map is the sum of HP and Hn minus P intersected with lambda plus or minus. Which is the same as the kernel okay, there's no more space here. This is the same as the kernel of D plus. The kernel of D plus intersected with this sum. Now the kernel of D plus is the kernel of D plus is the kernel of D intersected with lambda plus. Actually, well, what does this mean? This means intersected with the sections of lambda plus. Okay, now what is the kernel of D? Well, exactly. N divided by 2.
So we take the space twice.
Well, yes. Then for n divided by 2, we need to count it only once. Anyway, okay, let me put less than and plus plus dots. What are these dots? What are these dots? We'll see in a minute. Okay, so we have some contribution coming from the degrees other than the middle degree, and these cancel each other. So the only thing that matters is what happens in the middle degree. Okay, now does this formula make sense? So we have two finite dimensional vector spaces. We have alpha, which takes one to the other, and alpha squares to 1. Okay, so the eigenspaces which correspond to the eigenvalues +1 and -1 have the same dimension. What happens if alpha, if p is 1/2 n? Well, it depends on whether or not n is divisible by 4. If n is not divisible by 4, then, as we saw last week, alpha is I star. Now, the star squared is alpha squared is okay, alpha squared is 1. So the star squared is -1, which is basically something we already know from the formula for the star squared, which I mentioned last week. Now, star is a real operator, which basically means we have harmonic forms, but these harmonic forms are since the bundle is the complexification of the real cotangent bundle. The harmonic forms are basically the space of harmonic forms is the space of real harmonic forms tensor C. So the space HP is the same as HPR tensor C. And the operator is real. This means that this operator is induced by some operator from the real space to itself, tensor C. Tensor the identity of C. And what about the eigenspaces? Well, alpha has eigenvalues plus and minus 1. The star has eigenvalues plus and minus I. And the eigenvalue, the eigenspace which corresponds to plus 1 is the same as the eigenspace which corresponds to plus I think. Or is it the other way around? Let's see. It's the other way around. Okay, so if star something, okay, so the eigenvalues, the eigenspace of star, which corresponds to minus I, is the eigenspace of alpha, which corresponds to 1, because minus I times I is 1, and vice versa. So plus or minus 1 eigenvalues of alpha, eigenspaces of alpha are the same as minus plus I. The same as plus minus I eigenspaces of star. But since star is real, they have the same dimension. Why? Well, the star is real, and we know that every real operator has many the multiplicity of which eigenvalue is the same as the multiplicity of the complex conjugate eigenvalue for real operators. In general, this is not true, but for real operators, it is true. Valuza, does this make any sense? Okay, so I think that for n divisible by 2 but not by 4, we have proved that the eigenvalues, the eigenspaces of alpha, which correspond to plus and minus 1, have the same dimension. We have checked it for the direct sum of all degrees apart from the middle degree, and we have checked the same for the middle degree. So the index is index of d plus, which is the same as the index of d minus, is 0. If 4 does not divide n. Okay, but the signature of a not-dimensional manifold, by definition, is also 0. Now let's see what happens if n is divisible by 4.
So, can you please repeat what we did here? So, I understand every formula from the blackboard, and don't understand how this implies that index is 0.
Well, I consider d plus on okay, let me consider d on this sum. Then the this sum is preserved by alpha. It's the sum of the plus and minus 1 eigenspaces. What are the harmonic forms which so we want to calculate this harmonic forms intersected with the sections of lambda plus and minus. Now, what are these? My claim is these are precisely the plus and minus eigenvalues of alpha acting on H upper star. Well, or eigenspaces. And I want to calculate those eigenspaces of alpha acting on H star. First, I notice that alpha acts on this sum, which includes everything apart from the middle degree. There I have the plus and minus eigenvalues, eigenspaces, which have the same dimension. Well, because I have an operator from HP plus Hn minus b, which takes which interchanges these two subspaces and which squares to 1. And my claim is that the plus and minus eigenspaces are isomorphic. How to prove this? Well, are isomorphic to this space. Well, I construct an isomorphism by using this formula. And in general, it's just linear algebra. Если у нас есть какое-то конечномерное векторное пространство, то заводим программатические формы. Значит, конечномерное векторное пространство, и там еще одно, значит, оператор, который переставляет вот эти два, и у которого квадрат единица. Значит, спрашивается, сколько у него может быть собственное значение плюс и минус 1. Ответ, что в смысле там размерность собственных подпространств. Вот, значит, вот мы сейчас написали в явном виде собственное подпространство, и понятно, что они имеют одну и ту же размерность. Okay. Now it remains to calculate the eigenvalues or eigenspaces in the middle degree, and for n divisible by 2 but not by 4, the answer is again we have two eigenspaces which have the same dimension. And for n divisible by 4, we get something more interesting, namely alpha is the same as star. There is no multiple of I. Again, I take P again equal 1/2 m. Okay, there are two symmetric bilinear forms. On the real HP. And the first one is just the form which we use in the definition of the signature. This is the intersection form. But on the other hand, the second form is the scalar product. It's positive definite. So star, which is the same as alpha, transforms the intersection form into something positive definite. And again, a basic linear algebra shows that on the plus, respectively -1 eigenspace of star, the intersection form, which is given by this formula, is positive definite, respectively negative definite. And so the dimension of +1 eigenspace minus the dimension of -1 eigenspace is the signature of the intersection form. And this is it. This is what we're after. Igor, does this make any sense? общем, задача из линейной алгебры. Вот, значит, у меня есть какое-то пространство конечномерное. Ну, в данном случае вот гармонический форм средней размерности. Да, значит, у меня есть вещественное, значит, тоже сейчас важно. Значит, у меня есть на нем две формы. Значит, про одну я знаю, что она положительно определена, а про вторую я, значит, знаю, что она не обязательно положительно определена, значит, у нее есть какая-то сигнатура. И, значит, вот эти формы, значит, связаны таким образом, что, значит, применяя звездочку или что то же самое альфа к одной форме, я получаю другую форму. Ну, точнее, ну, в каком смысле применяю звездочку? В том смысле, что, значит, одна форма получаю из другой, значит, заменой одного из аргументов на звездочку от того же самого аргумента. Вот, ну, давайте посмотрим. Значит, вот, значит, у меня есть значит, у звездочки, значит, у меня есть у звездочки что? У звездочки есть плюс один подпространство, минус один подпространство. Вот давайте я посмотрю, значит, вот эту форму пересечения на плюс один подпространстве. Вот, что у меня получится? У меня получится, значит, ну, там, если я возьму какую-нибудь форму омега, значит, звездочка омега, значит, у меня будет тогда омега. Значит, я захочу проинтегрировать омега, wedge, значит, омега. Но что такое омега, wedge, омега? Да омега, wedge, звездочка омега. Потому что подпространство плюс один. А вот то, что омега, wedge, звездочка омега, значит, дает положительный интеграл, да я уже знаю. Почему? Потому что вот эта штука положительно определена. Okay, so example. If I have omega inside the plus or minus one eigenspace of star or of alpha, which is the same, then the integral of omega wedge omega is the same as plus or minus the integral of omega wedge star omega. But this is by definition something positive. The integral. Okay, are there any questions? Okay, now let's see. So this was one application of the index formula, which is basically a formula which expresses the signature in terms of the Pontryagin classes. Okay, now I want to talk a little bit about the Serre duality because I mentioned it last time. But are there people here who are interested in the Serre duality? Okay, now the Serre duality is an analog of the Poincaré duality for coherent sheaves. Let's recall okay, let me be more careful here. Because sometimes people use the word pseudo-Hermitian. A complex suppose we have a complex analytic manifold with a Hermitian metric. Let's recall that we have a PQ decomposition we have the PQ decomposition, which I've written here, and using the metric so here the bar means the opposite complex structure, and using the metric we can identify this space with this the exterior power of the tangent bundle. Okay, now let's see. Well, first of all, let's try to review some facts from linear algebra. Well, suppose we have a finite dimensional real vector, no, complex vector space with a Hermitian form. By the way, does everyone remember what a Hermitian form is? Okay, now if we have a Hermitian form on V, we get natural Hermitian forms on the space V bar, which is the same space with the opposite complex structure, and on the tensor, sorry, on the exterior algebra, and so on. Okay, now I want to construct the Hodge-Star operator. Well, there is the real part of the Hermitian form is a Euclidean is a symmetric bilinear form on V, considered as a real vector space. Using the real part of the Hermitian form. Okay, now well, let me complexify this Hodge-Star operator. Now, the result will go from the from the complexified algebra to itself, or which is the same as okay, so this is lambda, and this is lambda. Okay. Okay. So okay. So this is lambda, and this is lambda, but those are two different lambdas. So this is a real vector space, and we take the real exterior algebra. But this is a complex vector space, and we take the complex exterior algebra. Okay. Let me put an R here and a C here. And these are naturally isomorphic. Okay. Now I have a Hodge star operator, and I complexify it. I get some other operator. Okay. But let's remember that this thing is a direct sum of lambda PQs, where basically I use the same sort of okay. So what do I get? I get lambda V plus V bar. So this is canonical, and then I can write this as the sum of lambda PQs, where lambda PQ is lambda P of V tensor lambda Q V bar. Okay, I have this operator which goes from this direct sum to itself, and I want to understand where this operator takes lambda PQ. Okay, and now I suggest we have a break, 20 minutes, and then we'll come back to this fascinating problem. But before we do, are there any questions? Basically, most of what we're doing is just the usual standard linear algebra from year one. No elliptic operators, nothing, just linear algebra. Okay, so let's have a break, and then at 6 we continue. Are there any questions or comments?
А вот вы письмо прислали про выбор времени семинара.
Да.
Вы там как-то написали нот, там выберите время, которое вам удобно, и поставили звездочки нот.
Нет, идея была в том, что все напишут, какое время неудобно, а все оставшееся удобно.
А, то есть это неудобно.
Списать все-таки неудобное время, да? Я просто так не понял.
Да, значит, просто если каждый там напишет какое-то, значит, одно время, которое, ну, в общем, идее это все не пересечется. Вот если все напишут время, которое наоборот неудобно, здесь значит, ну, его, по идее, должно быть меньше, поэтому если мы это все исключим, то может быть что-то получится.
Да, и во-вторых, это на несколько недель, да?
Ну, так, значит, ну, в общем, такой план на ближайшее время это доказательство теорема приоритетического оператора, который мы вот сейчас во все используем. И, значит, дальше, ну да, и дальше нам еще нужно, чтобы понять категорию. В общем, да, это да, на несколько недель. Про категорию мы так ничего не поняли, правильно понимаю? То есть у нас что-то было такое, категория, но что это такое-то мы толком не знаем. Ну хорошо, да, значит, категорию нам нужно будет изучать, ну, там, хотя бы в каком-то объекте.
А вы микрофон выключите на время перерыва все-таки?
Что?
А вы выключите, наверное, все-таки микрофон на время перерыва?
Да, выключить микрофон, хорошо. Так. хорошо. Значит, тогда предлагаю... Так, предлагаю снова запустить запись.
Я ее не останавливал.
Ну хорошо. Okay, so we have okay, we have this this map star C, and we want to understand how what this map does with the components of this decomposition. Okay, well, first of all, let's let's try to understand what the complex conjugation how the complex conjugation acts on V tensor C. Well, this is a complex vector space, and why? Because we tensor something by C. And we use this complex structure, which comes from C. And then, since we have a complex vector space, we can take the complex conjugation. Okay. Now, the complex conjugation transforms a complex subspace to another complex subspace. And the question is, what happens with these two subspaces? Well, let's recall what these are. Okay, so V is the eigenspace of capital I, where capital I is multiplication by I, but viewed as a map from the underlying real space to itself. Okay, now is it a plus or a minus? Let's see. So if I apply I get Ix plus x
Both subspaces are isomorphic to V, but plus or minus depends on what you want to make.
Okay, so let's see. So I want to so I want V to be the eigenspace of which corresponds to the eigenvalue small I. Okay, so okay, I apply I to x minus I x, and I get I x, and then okay. So I have this these identities which shows that indeed the sign is minus. Okay, now what happens if I apply the complex conjugation? Well, I get the same to this expression. I get x plus ix. Where by x I mean x tensor 1. Okay, so the complex conjugation interchanges V and V bar, which is not surprising. Okay, now for similar reasons, lambda pq goes to lambda qp under complex conjugation, the same complex conjugation, namely the one obtained from this factor. Well, now let's look at the star. Well, the usual star takes lambda p to lambda 2n minus p. No surprises there. What about the complexified star? Where does the complexified star take lambda pq? Well, not quite. Let's see. But almost. well, my claim is it's the other way around. N minus q, n minus p. Or is it what you said?
Я так сказал, да.
Okay, then we agree. So n minus q, n minus p. Okay, well, this is again something from linear algebra, and do you want to check this in detail or not? Well, I suggest we don't want. No, maybe we do, but I suggest we don't. So maybe we do want, but I suggest we don't. We don't check it. Although, let's see. So. There is another operator which is which will be more useful for us. The bar of the star. What is it? It's basically apply the conjugation first, and then apply the star operator. And then we end up in lambda n minus b n minus q. Okay, is there any non-painful way to check this? To check that this, if we start here, we end up here. Non-painful meaning without without any long formulas or complicated expressions of any kind whatsoever.
To use the properties of star that alpha wedge alpha wedge star beta is proportional to the William form.
Okay.
So the William form is in lambda n.
Okay, so the volume form indeed is inside lambda and n. Or in other words, inside the top degree of this algebra, but the top degree of this algebra, but viewed as a real algebra. Okay, so this is and after we complexify, we get lambda n tensor lambda n, and if so if okay, now suppose I have lambda p lambda PV wedge, sorry, tensor lambda Q V bar, and what's although hold on. So I want this operator to preserve I want this operator to
Чем плохо мой план все-таки?
okay. So so
Знаем, что альфа внешне на звездочку бета, это когда давление бета на килограмм.
Ну, а форма объема наш.
Да, лямбда n. Вот.
Что?
Ну, она лямбда n лежит, если не
Так мы в любом случае лямбда n получим.
ну, сейчас, значит, лямбда n, но тогда значит, здесь непонятно откуда, значит, почему происходит перестановка.
Ну, сколько почему не получается? Ну, может, это и не так.
Вообще, по-моему, для вот этой звездочки можно просто явную форму написать в координатах.
Ну да, вот можно написать явную формулу в координатах, но хочется, значит, хочется понять, все-таки, значит, без явной формулы, значит, как же быть.
Сейчас. Дело в том, что обычно-то звездочку определяют так, чтобы вот это свойство сохранялось как раз-таки. В общем, но там, если ее определять комплексно, тогда надо, чтобы с чертой брать это внешнее произведение. Там альфа берут внешнее звездочки, бета с чертой. Вот. А как
Ага, да, правильно. Значит,
там может n минус p получиться.
сейчас. Okay, let's think a little, and if it doesn't work, then let's just say it's an exercise. I want to have this formula because I will shortly want to know that this star commutes with the Laplacian operator and so on. Let's see. Okay, I encourage everyone to check this formula at home, and if you arrive at a different conclusion, please don't keep it to yourself. Let us all know.
Вроде все верно. Минус v минус v.
Okay, let's say this is an exercise in linear algebra, and I suggest, well, by the way, I don't think it's a very difficult exercise. I suggest we all try to think about it later, and now we go on. Ну, по-моему, вот здесь меняются, а когда мы еще раз делаем сопряжение, то они становятся обратно.
По-моему, все правильно у нас написано.
Okay, so before we move on to holomorphic vector bundles, I want just to say that we have an operator so if X is if X is a manifold, we have an operator we have suppose we have a complex analytic manifold with a Hermitian metric. Then we have the star operator and star C and bar star C. And my claim is that what do I need? I need this operator to to commute with the Laplace operator. I think this is all I need because later on I will want to. Yes, I think this is. Okay. I need the following thing. This operator commutes with the de Rham operator and with the Dolbeau operator plus the joint up to multiplication by something. And this something is a multiple of I. I don't care which multiple, honestly. Some multiple. Now well, the first claim is straightforward. If since star commutes anti-commutes with delta plus, or in fact no. The star commutes up to multiplication by something with de Rham plus the joint of de Rham. It's the formula which I mentioned earlier today but didn't prove. Okay, now let's see what happens when we apply a d plus d conjugate. This operator preserves every vertical line of the PQ plane. Oh, sorry, no. But actually, if I didn't, these are the operators which I will need. But if I didn't write the bars, the claim will still be true. Basically, by looking at what happens by looking at what happens on every lambda PQ, we get, and by using this, we get the same statement for the Dolbeau operator. Okay, now let's see what happens if I have a holomorphic vector bundle. Then we have the Dolbeault operator, which goes from from sections of this vector bundle to itself. Okay, now similarly, I can define the well, basically, this is something we saw already, and if we want, we may as well multiply here by we may multiply everything by some exterior power of the T upper star of x without the bar. Okay, now now I want to define an analog of the star operator, but for bundles. And here I have a problem, because this map is complex linear. This map is anti-linear. Why? Well, because the conjugation is anti-linear. If I want to map from anyway, the operator which I have here, the star operator, is anti-linear. So I need to change the bundle with the bundle as well, and I do the following thing. Using the metric, I can identify E with the dual of E, but in an anti-linear way.
Is it the same metric, same Hermitian metric on manifold, or some other?
Some other metric. Let's. Some other metric, because if I just have a metric on a manifold, it doesn't give me a metric on the bundle in any meaningful way. So I want to do what I want to do. Basically, I apply tau tensor star C bar. So this is an anti-linear map from this bundle to this bundle. Okay, and star C is an anti-linear map from this bundle to this bundle. Oh, by the way, there's a missing bar. Okay, now I can tensor multiply two anti-linear maps. I cannot tensor multiply a linear map by an anti-linear map, which is why I need something anti-linear in the first argument as well. Okay, now I have all ingredients, I think. Okay, now now we did the same thing we did when we proved the Poincaré duality theorem. But the only thing which is missing is okay. Let's try to remember what we did when we proved the Poincaré duality theorem. We applied the star operator to harmonic forms, and then we used the fact that the star operator is an isomorphism between harmonic forms in this degree and harmonic forms in that degree. We want to do something similar, but let's remember what harmonic elements correspond to in this particular case. And now there's something. Okay, so there's something which is missing here. Okay, so there's okay, there's one ingredient missing in this formula. What is it? Let's forget about E for a minute.
So in reality we need holomorphic key forms.
Well, let's forget about E for a minute. Then we must get this operator back. Okay, so here we have P, Q, then N minus P, N minus Q. And well, N minus Q, we have it. But N minus P is missing. Okay, let me reinstate it. Lambda n lambda n. Why? Well, because Q P is in this particular case P is 0. So I have lambda n of T star x, which is the canonical bundle. Okay, now it's there. And by the way, this shows that this explains where the canonical bundle comes from. Okay, now this elliptic complex calculates the cohomology of x with coefficients in E. Now, what about this one? Well, okay. Well, this one calculates the cohomology of x with coefficients in lambda n. Okay, I'll write it here. N minus star of x with lambda n t alpha star x tensor E star. Okay, no, I want, okay. h n minus star x. Okay, let me write it like this. E star tensor lambda n t to star x. So this complex calculates the cohomology of this bundle, and basically we get this air duality. But let's look at the formula once again. We want to show that this operator star C E conjugate well, sort of commutes with the Laplacian. Let's see in which sense it commutes with the Laplacian, because in fact we have two Laplacians. We have one Laplacian for this. We have one Laplacian which calculates the cohomology of this bundle. And another one which calculates the cohomology of the other bundle. Now, what do these Laplacians have to do with the star operator? So this time we have not one Laplacian, but two Laplacians, and we want to know how these are related. Let's think. Well, it's pretty straightforward. We have not.
Like for D in ground
Yes, but we actually we don't need an exact formula. All we need to know that this star operator takes forms which are harmonic with respect to this Laplacian, to forms which are harmonic with respect to this Laplacian. And what do we know? We know that let's assume that we know we know this formula. The low Laplacian commutes with the star. Now. Now, um, now I want to write the Laplacian for with a vector bundle in terms of this this one. Let's think. Or is there maybe an easier way to do this? Let's think. Мы хотим понять, почему вот эта вот звездочка переводит значит, такие гармонические формы в такие гармонические формы. Ну, в принципе, значит, более-менее понятно, куда копать, но сейчас, значит, сейчас что-то разумного какого-то объяснения я не могу придумать. Let's think a little. Let's temporarily forget about, maybe not. Okay, so we have the Durham operator D, and I also have the D bar plus D bar conjugate, which is the Delbow operator, and I want to express I want to express I have this this identity, and I want to use it somehow. Okay, so this is a component of this. Okay, now
Ну, Гриффитс и Харрис, они просто вводят, пишут, что вот этот сопряженный d-бар это минус звездочка, d-бар звездочка.
да, это я знаю, но
И вопрос про то, что они коммутируются звездочкой, игнорируют.
значит, ну, значит, хочется, ну, в общем, хочется это все понять, значит, не как Гриффитс и Харрис, а по-нормальному. Но, значит, я сейчас, в общем, значит, сейчас у меня там вменяемого объяснения нету, значит, ну, значит, давайте, значит, или давайте все подумаем, или давайте скажем, что, значит, ну вот сегодня вот этот момент нам понять не удалось. Так, хорошо. В общем, значит, нет, значит, вот этот вот момент остается по знакам вопроса. So this part remains a question mark, namely why the operator takes harmonic elements of the kernel of this Laplacian to the elements of the kernel of this Laplacian. It's not massively difficult, but I'm just tired and I need to think about it. Okay, apart from this, are there any more questions related to this duality theorem? Okay, now do we want to start a new topic? We still have, we still have a few minutes left. Or maybe it would be better to discuss something related to what we've seen today and start something else next time.
Consider this to be true. Then what we do next?
We consider what to be true.
That star sends harmonic forms to harmonic forms.
Well, then we have an isomorphism between these groups and these groups, which is what we're after. And this isomorphism is given by the star CE. So very briefly, the main idea. the CR duality is an isomorphism between something and something. And those both somethings are the cohomology groups of some elliptic complexes. For the first something is this complex, and for the second something is this complex. And then we have harmonic representatives for each cohomology class. And then we have a map, namely the map given by the star operator, which takes harmonic representatives to harmonic representatives. And it's an isomorphism, well, basically because well, because star, well, this star is an isomorphism, tau is an isomorphism, and the well, if we apply the map twice using actually, the fact that the map is an isomorphism can be checked fiber-wise. Why? Well, because star is and star and its analogs are maps of vector bundles, and basically we need to check on the level of vector spaces that a map from W tensor lambda q v bar to n minus q v bar. Basically, the stalkwise analog of this formula is an isomorphism. But this is again linear algebra, which is something that that we systematically sweep under the carpet. Okay, so we have well, we have an isomorphism, and okay, we have an isomorphism of vector bundles. Okay, now this isomorphism takes harmonic sections to harmonic sections, or harmonic elements to harmonic elements. Then the induced map is between the spaces of harmonic elements is also an isomorphism. Let's think about this. Yes, but then we hold on.
So
Well, yes. So you propose to have here another an arbitrary power of this bundle, and then use the same or the inverse of tau to construct the map in the opposite direction, and then we have yes, and then we have basically constructed an explicit inverse map. Okay. Yes, but let's see if there is. Okay. Anyway, this I think this would work, but let's. Let me think a little more about. Okay. Yeah. I think there's. There is no way to avoid having to construct an inverse map, because otherwise we get injectivity for free, but subjectivity is somewhat more trickier. Okay. Are there any more questions, remarks on this story?
actually, we have chosen two metrics on X and on Y.
Yes.
And in algebraic geometry, third duality doesn't know anything about metrics.
True, but but nothing basically.
So the question is this our construction of third duality canonical?
Well,
this construction is actually obviously not canonical, because canonical construction is pairing between these spaces.
Well, there are some choices which were made, and yes, we did choose a metric and two metrics, and let's see if the so we need basically we need to compare two the results for two metrics. On the one hand, obviously the results are isomorphic, because every two because the space of metrics are contractible. And why is it contractible? Because it's a convex subspace of some vector space. By the way, in algebraic geometry, we also need to make choices, but they don't pose as many problems because well, what choices? Well, we need to define the cohomology of a sheaf. Then we need, for example, an injective resolution. Well, there is a way to functorially resolve all sheaves, and this is why one can't forget about this problem. But there may be several ways of canonically resolving all sheaves, or there are other injectively resolving all sheaves, or there are other ways to resolve sheaves. For example, instead of injective resolutions, we could use Flabber resolutions and so on. And we get a result which is different but canonically isomorphic. Now. Okay, here is what happens when we resolve the bundle E using the Dolbeau resolution. We get something canonical. The Dolbeau resolution does not require a metric. But then we need a metric to have an elliptic operator. For different metrics, we will get different subspaces of harmonic elements. So we have this elliptic complex, and inside the sections of these bundles, there will be spaces of harmonic elements which will vary from metric to metric. They will have the same dimension. Why? Because they're all isomorphic to the cohomology groups of the sheaf. But the spaces of harmonic elements will themselves be different, but they will all live inside the sections of this bundle. And since the space of metrics is contractible, we can choose a unique, a preferred way to identify any two such subspaces. Значит, то бишь, значит, для разных метрик будут получаться разные подпространства гармонических сечений, но любые два таких подпространства можно отождествить. Так, есть ли у нас еще какие-нибудь там вопросы, комментарии и так далее? Well, it looks like there aren't any more things we want to discuss today, so let's call it today, and then